Welcome to Learning Chemistry with Faye. In this video, we'll talk about Hess Law. So Hess Law is really just learning the relationships between the chemical equations. If you can see how they can add and subtract kind of like math equations. For example, in a chemical equation, if you have a cup of reactants, okay, let's just say, give an example as A plus B to form a C with its enthalpy equals to a specific number. Let's name it enthalpy 1. Okay, so let's say it's equal to 2000 kilojoules. And you have another reaction with a similar reactants, but this time you have something slightly different. Let's say it gives you some a product P2. Okay, so now you wanted to look your final. So let's give the second reaction another enthalpy of reaction. Just to make the math easy, I picked some easy numbers for us to process. And my final product is something along the lines of 3A plus 2B plus D equals, and my products, what I want, are 2C and 1P2, whatever that is. Then how can we determine the enthalpy for this final reaction using what we already know? So you really just kind of break down your reactions, your final reactions, to see what are the components that can fit, or what are the components that match what you are already given of. So in this case, if you look at there are 3 A's and I have 2 B's, so I need to multiply the first reaction by 2. So if I'm multiplying this first reaction right here by 2, so this first reaction right here by 2, then I also need to multiply the enthalpy of the first reaction by 2. Okay, so let's go ahead and multiply this one by 2. And then we're going to multiply this math also by 2. And then if we kind of figure out all the sum of your reactants, now you have 2 A's from the first reaction and 1 A from the second reaction, and you have 3 A's total, right? So that's the 3 A's we have in the product. And with the multiplication of 2 and B, you can do 2B, and that's where you end up with a 2B. And you also have 2 C's, right? So you remember this multiply for the entire reaction, not just a specific compound, not just one reactant, so don't get it confused. So what you might want to do to make it less confusing is by writing a parentheses of the entire reaction. Remember, this multiplier applies the same because your enthalpy is the enthalpy of the entire reaction. It's not just to a specific part of this reaction. Okay, so same with the second. And it looks like our second, since we only need one product 2, 1D, one more A than what the first reaction had given us. So we can just keep this the same, right? And now what we're going to do is now we notice we're adding both of these equations, both of these chemical reactions together to produce our final reactions. Then what we wanted to do is we wanted to add the equations, add the chemical equations, and also add the delta H's, right? So we also want to add these enthalpies. But remember, our very first enthalpy has to multiply by 2 first. So in this case, our enthalpy for our final equation is equal to 2,000 times 2. So we have a 4,000 plus 1,500. And here we would have 5,500 kilojoules. Okay, so what about if my final product looks something like this? I want my final product looks something different. It's going to look like B plus P2 to give me D plus C. So what happens if this is my final reaction that I actually wanted? Then you have to look differently at the relationship of this entire reaction, these reactions that are given, right? So first, what you wanted to do is you always wanted to look at what's on your product side. So in this case, you have a C, which is right here. And then that means that they're on for the first reaction, you have it in the correct order. Your reactants should be on the reactant side of your final reaction, and your product should end up on the product side of your reaction. But what about the second reaction? And then we can notice that the second reaction, the reactant, ended up on my product side, and my product ended up on the reactant side. That means in order for me to calculate the enthalpy for this reaction, I need to reverse the second reaction. Whenever you are reversing a chemical equation, you do the same thing to the enthalpy, not by dividing or adding or anything, but add a negative sign to your enthalpy. So in this case, if we add these two, I'll just write it down here. So we have, let's say A plus B give us C, right? So we have A, let me write in something slightly that's easier to read. Okay, so we have A plus B to give us C. And we have to reverse the second reaction to turn it into something like product 2 A plus E. And whenever you're adding the first reaction to the second reaction, you kind of add it almost like the math equations. So if whatever ends up on the left side and whatever ends up on the reactant side and the product side are the same thing, you cross it off. So in this case, we have this chemical A, right? This compound A on both sides. So we cross both of them off and then add the other two together. So right here we're adding the B and the P2 together. So we have a B plus product 2, and then we're adding the C and D together, and then we have a C plus D product side. So that means for our delta H, for our enthalpies, what we will have to do, we will add delta H1 as the same, right? So we just keep it at 2,000. But we had to reverse the second equation, second chemical equation. That means our delta H2 now is going to be negative, Okay, so in that case, we're going to subtract the 1500 kilojoules. And for this chemical equation right here, we will have 500 kilojoules for this particular, for the delta H, for the enthalpy of this reaction. We will name it enthalpy 4. Okay, so let's go over a couple of exercise. So for example, we are looking for the delta H. We're trying to predict the delta H values for 3N2 plus 3O2 to produce 6NO. All right, and we're given this very first reaction, which is nitrogen plus oxygen to give us a 2NO. And then we have the second reaction, which is 2NOs plus O2 to give us 2NO2s. Remember, you don't have to always use every single given information that's provided on the piece of paper. You just need to use whatever that you need. So in this case, you wanted to, again, start with the product to see what matches your product. And you can quickly find you have 1NO on this side, on the product side. Actually, you have 6NO on your product side, and you have 2NOs on your product side of your very first given equation. So that means you don't really need this second chemical equation right here. So you only need to find the relationship of what the first chemical equation, this is a thermochemical equation, that's given you to the relationship of your final product equation. Okay, so you probably can notice that the N2 turning into 3N2s, O2 turning into 3O2s, and 2NOs turning into 6NOs. That means they're all in multipliers of 3. If that's the case, what we can do, we're going to multiply the thermochemical equation that was provided to us all by 3. We multiply everything by 3. That means the reactants is going to multiply by 3, the product is going to multiply it by 3, and so are the enthalpies as well. And we will end up with 180.4 kilojoules multiplied by 3, which this final equation that we're looking for, the enthalpy for it, is 541.2 kilojoules. Let's go over another example. If I am giving the same two equations, same two thermochemical equations, and this time I am looking for 2NOs, 2NO2, NO gas to produce N2 plus O2. And then we're looking for whatever is on my product side. Always start with the products that's for your final equation. And then if you notice the products of what you're looking for, of the chemical equation that you're looking for, it landed on the reactant side of your very first chemical equation. That means, again, we don't really need the second chemical equation. What we need to do is reverse the reactant and the product of your first chemical equation, right? So we just simply switch them. If you switch the reaction, remember you need to switch the sign of your enthalpy of reaction. So in this case, what was given for a chemical equation is 180.4 kilojoules for the enthalpy. In that case, we just need to reverse it. Reverse both. Remember, when you reverse, it doesn't mean to divide or to multiply or to do anything. Do not reverse by dividing it by 1 over. Reverse means reverse sign. Okay, so you will have, instead of being your chemical equations is given your chemical equations needing 180 kilojoules for the reaction to occur, you are going to give 180 kilojoules. So that means you're going to have a negative 180.4 kilojoules. Let's try one more. So now we know the relationships between these reactants and products can be multiplied, can be reversed. What else can we do? We can also subtract and add, just like a math equation. For example, same two thermochemical chemical equations are given right here, and now we are looking for this third chemical equation right here. Again, we're going to start with our product, right? So we are going to start with our product of what we're looking for, of the chemical equation that we are looking for. In this case, we have 2NO2. That looks exactly like the second equation of our second equation of what was given to us. However, but if you look at the reactants, they are not the same as the second chemical equation that's given to us. That means we have to do something about this in order to form the final reactions that we wanted. So how do we do that? Then we now start looking at the reactants. What are we looking for? So we want two O2s. We want N2 to end up on our reactant side, but we want to dismiss the NOs, right? The two NOs on our reactant sides for the second chemical equation. So what we will do, we will simply add both of these equations together. We're going to add them up. Remember, by adding the chemical equations up also means you're going to add the enthalpies of the reactions up as well. So by adding these two up, you can cancel any compound that's on the reactant side and on the product side, that's the same. So in this case, we have 2NO on both the reactant side and the product side. So we can just cancel them out. And then now you're going to add up everything else like a math equation. So I have one nitrogen, then I'm going to copy it down directly to my reaction I'm looking for, and I'm going to end up with two O2s, and I'm going to end up with two NO2s. So they add up perfectly to what I'm looking for. Then in that case, I'm going to do the same thing to my enthalpies, my delta H's, from what I have, right, from the equations that was given to me. So in this case, I'm going to add 180 subtracting 114 kilojoules, right? So, or you can think of it also as 180.4 add negative 114.0 kilojoules. And that will give us, so here are the nitrogens, the oxygens, and then will give us the final product. And then you're going to add these two. Remember, if you have a negative sign, your add sign, when you have one plus sign, one negative sign, you are just simply going to switch it to subtract. If it's a negative, then you'll have a positive, okay? So in this case, you will have 66.4 kilojoules. So hopefully this will help you understand the relationships between the chemical reactions and enthalpies according to them, and how you can use this relationship to determine the chemical equations that you are looking for, okay, and the enthalpies that you are looking for. If you have any other questions, feel free to leave a comment, and I will see you next time.